Hello, everyone, and welcome to the VaNTAGe seminar. So we're starting fall 2025 with a series of talks on profinite groups and Galois groups. And today we're very happy to have Noémie Combe, who will be talking about Grothendieck path integrals. And there will be some natural breakpoints in this talk where you can ask questions. So, Noémie, is it okay if we record this talk?
Yes.
Oh, great. Well, please go ahead.
Okay, thank you for the invitation. So I'm going to talk about Grothendieck path integrals. So the goal of my work here is to give a non-tautological, non-trivial description of the absolute Galois group. So for instance, Gal Q bar over Q. Q are the rational numbers. And so this work will be based on some works and conjectures by Grothendieck and the so-called IOM conjecture. So it's Ihara Oda Matsumoto conjecture. So in this work, in this talk, I propose a new approach using tools arising from Cantor sets and a construction which will be inspired from Feynman-like path integrals. And so let me start with first the context and presenting the situation with Grothendieck's pioneering question. So it's an enigmatic conjecture from the 80s and its developments. So in particular, one of Grothendieck's ideas in his Esquisse d'un programme was to give a description of the absolute Galois group for rational numbers via something that we nowadays call the Grothendieck-Teichmüller group. So this is the profinite version. And a pro-unipotent version exists also, although I will not be talking about this in this seminar. So let me go back to Grothendieck's idea. So Grothendieck noticed that the absolute Galois group Gal Q bar over Q acts upon the algebraic fundamental groups of all stacks MGN and the natural maps relating these for various genera G and marked points N, forming thus a tower. And so the conjecture was that the absolute Galois group Gal Q bar over Q coincides with the symmetry group of this profinite completion. So this is actually an idea which was quite natural if we go back to, a theorem that he wrote in SGA1. So the algebraic fundamental group pi1 alg here is denoted on the upper right side, and it has an action of the absolute Galois group Gal Q bar over Q. So quoting the exact theorem, so I have put the entire reference. V is a quasi-compact and quasi-separate scheme over Q, then there exists a short exact sequence of profinite topological groups. And this short exact sequence is outlined in the middle of this slide. So I wrote some reminder about profinite completion, profinite groups. So we have a limit of finite groups. G is isomorphic to this limit of GIs. So GI has discrete topology. And the meaning of algebraic fundamental group, it's simply that it's a fundamental group for a scheme. So it is the fundamental group seen through the eyes of étale homotopy. So basically everything comes from this short exact sequence. And there have been many very interesting developments. In particular, in the 90s, there was a beautiful result by Drinfeld, where he introduces the object that we nowadays call Grothendieck group, the perfinite group, and which encapsulates symmetries of the perfinite completion mentioned earlier, where we have the following relation. So gal q bar over q injects into gt hat. And so the very mysterious side of this is that the Grothendieck group, well, it's more of a topological object, a geometric topological object, and it acts on a very wide variety of objects in many different fields of math. So that's why it makes it actually central, not only for number theory, but, well, people working in, well, mathematical physics or more in geometrical branches are also fascinated by Grothendieck-Teichmüller group. And, well, the heart of this is that it remains quite mysterious. So the structure in relation to many of the object it acts on is actually unclear and forms ongoing research. So there's a lot of, well, possibilities of tackling this problem and, well, trying to say something non-tautological about gal q bar over q, about gt hat, and possibly any related objects. So that's why we're so interested in that. And so this was Grothendieck's initial idea, but there were further developments, in particular on the side of Ihara and Oda Matsumoto, who formulated what we call a IOM perfinite conjecture, which goes beyond what I said before for arbitrary fields. In particular, K0 can be the field of rational numbers. So everybody's goal here is to give perhaps a topological, maybe combinatorial, at least topological and combinatorial description of what's going on in this absolute Galois group, Gal K0, so over arbitrary fields. In particular, if we want to go beyond that, there exists a stronger version for a pro L version given by Florian Popp of this IOM conjecture. So now I'm going to explain a little bit this broader context. Okay, so K0 is a fixed subfield of the complex numbers, and K is going to be the algebraic closure of K0 inside complex numbers. Let x bar be the base change to K of x. So x bar is denoted x times K with index K0. And just similarly, as I just wrote previously for the Grothendieck SGA, there exists an exact sequence of Ital fundamental groups given in the blue box. So 1 goes to pi1 x bar, goes to pi1 x, goes to gal K0, and back to 1. So this is a more general formulation. And in particular, we are going to define a category, G indexed by out, where objects are profinite groups above gal K0, which means that we have diagrams of continuous morphisms of profinite groups, which have the shape P is maps G to gal K0, and morphisms are continuous outer morphisms above gal K0. Okay. So this exact sequence actually gives rise to a representation. So it's exactly as I said for SGA statement. So we have a representation of gal K0 into the outer automorphisms of what I denoted pi bar of x. So it's simply that I'm going to consider algebraic fundamental group for x bar. And, and that's mainly the objects that we want. Now, by the functoriality of pi1, the collection of all the representations is compatible with the base changes of K0 morphisms, f from x to y, of geometrically integral K0 varieties. And in particular, for every small category V of geometrically integral varieties over K0, its algebraic fundamental group functor from V to G out gives rise to a representation given as follows. So Gal K0 is mapped to automorphisms of pi bar V. And automorphisms, so we're just considering automorphism group of pi bar V. So that's the more general context of the story. And so now if we want to go back to Grothendieck, so the story goes as follows. We want a new description of the absolute Galois group by finding categories V for which rho V maps Gal K0 injectively into the automorphism of pi bar V. And we want that the image of rho V in this automorphism group has actually a nice description. So that's what it's all about. And so if this is true, then via the isomorphism rho V, we would have a new non-tautological description of this absolute Galois group. And so that's what we want. So if K0 is the rational numbers, is the field of rational numbers, then Grothendieck's suggestion is to study pi bar V for V subcategories of the Teichmüller modular tau or T of all the moduli spaces MGN. So for instance, if V0 is given by the moduli spaces in with a small number of marked points, M04 and M05, then we get actually the famous Grothendieck-Teichmüller group, GT. So this is how we recover from this more abstract and categorical formalism, well, the GT hat that was previously, well, at the beginning introduced by Grothendieck. And that's what the IOM and Grothendieck conjecture is about. So first aspect of things is the nature of this morphism, rho V. And actually concerning its nature, very little is, well, little is known actually. So if we have K0 equals to the rational numbers, well, by Drinfeld, we know that rho V is going to be injective, provided we take the projective line minus 3 points. But then there have been different developments. So for example, Vojevodsky showed the same is true if we take X to be an affine open in a curve of genus 1. And then Matsumoto showed that the same holds if X is some affine hyperbolic curve. And Hoshi Mochizuki showed that rho is injective as soon as V contains at least one hyperbolic curve. So yeah, so that's the developments for if we're talking about the injectivity of rho V. So it's less understood. And Ihara in the 80s asked whether rho is an isomorphism. Provided K0 is Q, well, we recover Grothendieck's conjecture. I'm sorry, I have a cold, so. So based on some motivic evidence, we have then the conjecture of Oda and Matsumoto that the answer should be actually positive. So based on their own well vision, the answer was positive. So there's a paper by Florian Popp where he gives well, he makes a proof that IOM is positive for even more general fields, thus giving a positive answer to IOM. And the last thing is that there was further development by Yves for p-adics, and well, he suggests constructs a construction where we can actually translate all this to p-adic setting. And so apparently all this would hold also for p-adic fields, which I won't investigate in this talk. And so I propose here actually a new viewpoint, which is via Cantorian tools and Polish group perspective. So it's in this paper. So from my construction, so I just work on the traditional, let's say, Grothendieck conjecture, where the field is the rational numbers, and you can prove very nicely that all these are Cantorian sets. And part of my goal is actually to give maybe a different description for Gall Q bar over Q and for Grothendieck-Teichmüller group, well, via this tool of Cantorian sets. And well, everything will nicely generalize also to the p-adic setting because you have a lot of Cantor set geometry there. So I think it could also extend beyond actually. So here it's more of a proof, a sketch of proof that we have Cantorian sets on both sides and the Galois and the GT hat. As far as Galois group is concerned, well, you can give many different proofs. So I did my own proof. It's not the shortest one because I was really interested in analyzing what's going on in the absolute Galois group. So my proof is very, very long, but I want actually to describe every element of the absolute Galois group as a kind of Cantorian path. That means an infinite sequence, a binary infinite sequence by zeros and ones, and giving a rule how to describe this path via the Cantor set situation. So that's why my proof is not 2 lines, but maybe more. Okay, so GT hat is also a Cantor set. And so my proof was based just on profinite groups and statements there. So basically, I'm using the fact, so F2 here will be a profinite completion of the free group in 2 generators. And the fact that the automorphism of F2 hat will be a Polish group. And well, and in the end, I can prove that GT hat is actually a Polish group itself. So F2 hat has this kind of definition. And I want to also, there's the same philosophy, I want to use this kind of, description in order to describe every element of GT hat and the Galois via this infinite binary sequence and see whether, how this matches together. That's my question, how this works together. So that's why I do this. So I'm just like explaining why basically you have a Cantor set. So every totally disconnected, locally compact Polish group must be one of the 3. So it could be a discrete space, It could be a Cantor set, or it can be a Cantor set times natural numbers with product topology. And well, it's going to be straightforward that it's clearly not a discrete space, and that clearly, well, it's not non-compact, therefore the only possibility is to be Cantorian. So it's uncountable but compact. So that's actually a conclusion. Why is it this way? So pros and cons. So pros is that I'm going to use the Cantorian tools to try to say something which is not maybe trivial about Galois and GT hats. Well, the cons are that some arithmetical data can easily get lost because Cantorian tools are Cantorian tools. We're not talking about number theory. So I'll have to recover all the arithmetical lost data via, well, supplementary things, additional things, and that's how I'm going to use something that I call Grothendieck path integral, which is inspired from the classical Feynman path integrals here. So I'm going to do an adaptation. So that's the question. How do we recover lost arithmetical data? Yeah, so I said we can ask questions. So that's the right moment because this is part 2 about path integral. So if there are no questions, I'll continue. So this beautiful formula is the classical Feynman path integral definition. So usually we'll have exponential of I times something called an action. Gamma is an element there. H bar will be some parameter, and we need some measure mu, which is usually as such not well defined in the classical literature. But in our case, everything will be very nicely defined. So that's the Feynman path integral. And so I'm going to adapt the definition to my setting. So I'm going to consider the space G, which will be my Cantor set, which will be this absolute Galois group, or GT hat, since they're both Cantor sets. And we know that they can be equipped with a normalized Haar measure, mu. And so my claim is that there exists a generic path integral formulation for G, providing a novel arithmetical framework inspired by Feynman path integrals, which looks like this. So mu is going to be a normalized cylindrical Haar measure. So this is coming directly from the Cantor set story. And because we're in a context of profinite groups. And now the hard work is going to be about defining something which is an arithmetic action. So whatever that means, it means that we need to define some functional of a quadratic form. That's what the physics requires. So I'm gonna have to introduce some quadratic form that will be maybe interesting for recovering some arithmetic data. So usually people in physics take h bar as a deformation parameter. I'll simply ignore this here. And gamma is going to be, well, a Cantorian path. It's going to be an element of the absolute Galois group or of GT hat. And it can be this binary sequence that I'll define at the end of my talk. And so all this is well defined because of the geometry, because of this harmonic analysis coming from these profinite groups. This is well defined, actually, all this here. So I'll skip the proof because I think there is no issue with this whatsoever. It's in my paper, and I think it's in fact easy to prove it. The big question here is, okay, but how can we use this to provide some arithmetics which are interesting? So as I said, the main issue is to define something that I call arithmetic action functional, which will be well, a value for number theory. So my paths, this is easy. We said that we are in a Cantorian set, so we can define Cantorian paths. And these are elements in GAL-Q, because I'm starting just with GAL-Q for simplicity. The functional S assigns a weight. So that's the philosophy. We want to assign a weight to each Galois automorphism. And if we want more information about the measure, well, this is thanks to the prefinite group setting, which is very nice, that there exists normalized harm measure on the prefinite group, which is going to be cylindrical. And cylindrical refers to this kind of sets. So that's a lemma. This is a technical lemma. I will skip the proof because I think it's clear from this geometry here. And the question is the arithmetic action functional? And I propose to construct it via a given pairing. So it's going to be this pairing. So I'm going to do an evaluation where C is going to be a class in H1 et al. Of X, Q over Z, where X is going to be a motive over Q. So this is actually, you can actually introduce another arithmetic action functional. There are many possibilities, but I chose this one. And this pairing can be well defined using Kummer sequence, or if we want to go a bit more general, via evaluation of cocycles in Galois cohomology. So this is for me what I found most hard to well find. So to give a bit of an idea of how it goes, I'll be considering the Kummer sequence. And for my motive, I can take spec of Q. And given a positive integer n, well, we have a well-defined exact sequence of sheaves that goes as follows, where, well, mu n is not the measure here, but simply the group of nth roots of unity. And okay, and so the main thing here is that H1 et al. Will be, well, the Kummer isomorphism implies that you can write it as this quotient here. And by construction, the direct limit on the right is going to be isomorphic to this object Q with cross tensor Q over Z. And so that's how you can define this this pairing, actually. So this is what allows you to define the pairing. And so, okay, so to define the pairing, we can choose an element in Q bar such that we have beta m equals to a power k. And for sigma and gal Q, we have this pairing. Whereas log of this mod Z. So yeah, so this is just to say that, well, via this Kummer sequence, well, we can define well, there exists a well-defined pairing, and if you want to go beyond this kind of objects, well, it has to be a bit more complicated and use some Galois cohomology. So I'm not speaking about this here. So to summarize, there exists an object here that I call the Grothendieck path integral or Galois path integral, which mimics the idea that exists for Feynman path integrals, but which has as a purpose to give some arithmetical data concerning Galois or GT. Knowing that I have started with a Cantorian viewpoint, and I'm hoping to recover something interesting about GAL-Q and GT. So this integral is going to be, in fact, an indicator of rationality, because the way I chose the pairing is going to imply this kind of object. A value of 1 indicates that the class is invariant, that this class, C, is invariant under the group action, and is going to be 0 if we have a non-trivial obstruction. So it's a kind of Galois invariance criterion. So to summarize, if I consider G, my space, my contour space, to be the absolute Galois group here, I can equip it with a normalized Haar measure. And if I consider M to be a motive over Q, I'll consider class C in H1 of et al. And choosing in particular a pairing defined via Kummer sequence or evaluation of cocycles, this pairing gives, well, this pairing is bilinear and continuous and defines this following integral. So maybe some of you have guessed this map from sigma to this exponential is in fact a continuous character of G. And we have an invariant. I of C is 1 if this evaluation turns out to be 0 and 0 otherwise. So roughly speaking, and in other words, the pairing provides a Galois invariance criterion for all sigma and G. So if this class is G invariant, then, well, we have 1 in this. So it's a Galois theoretic detector for whether C descends to Q. So that's the Galois path integral. So now it's a bit of a discussion. So I said I was inspired by Feynman path integrals, and now I want to discuss maybe is there any relation between what I've defined, this detector of rationality, and is there anything to do with the Feynman path integral? And so that's what I'm doing this table. So this is an analogy table. So I have a space of paths. So these are continuous trajectories in the classical setting. My space of paths are just Galois automorphisms or Cantorian binary sequence. Then we have a fundamental object, which is this action functional, which is, so this is well defined for the physics world, but in my case, for the arithmetical world, I had to create something out of thin air in some sense. So I chose a cohomological pairing. And I think it does well the work. Okay, and then okay, we wanted to assign a value here. So this is more of a physics thing, a phase assignment, a quantum phase. In our case, it's maybe not so relevant. But we can call it an Artin type of phase. And the rest, it will just perfectly match. So you have a unit complex number, and we have roots of unity here, so it works. In the physics world, we have sum over paths which go like this. We can also create this as sum over Galois, so it works. Interference example holds also. Yeah, and so I think I've discussed mostly everything that was coming from the physics and the impact it has on arithmetics. Here we have some gauge invariants, and we have here Galois equivariance. So therefore, yeah, I have defined my rationality indicator. And this is just because I was in the Cantor setting, and so I could define this Galois integral. The question, of course, whether it works for GT hat. So the answer is yes, because we're again in this Cantorian setting, and well, it has also an interesting, well, it's also interesting to understand whether this could bring some information about GT hat and how it works with the one coming from Galois, the relations. Can we say something about that? Yeah. So in this case, we had some Q invariants of the class C. Here it's going to be also very similar. We're going to take an object that's going to be related to some art and motive and decide whether, well, the integral will tell you whether it is a trivial character and yes, whether it's some rational object. So for GT hat path integral, I will take in continuous homomorphism from Q to Q mod Z. So it's very similar to previously, but that's the way I constructed it. And so it's an element of H1 spec of Q. And as I said previously, corresponds to a character which will be associated to some art and motive. So class of psi denotes the cohomology class of psi in this H1 of spec Q. And well, as previously, the problem will be to define a pairing that makes sense. And so which looks as follows. So it will be defined as an evaluation of the character psi and element theta. And notice that here I'm talking about Q, although this is supposed to be GT hat path integral, but this actually is supposed to capture the Galois group incarnations as well within GT hat. And so that's why we have this object here, Q. Okay, and as previously, I have this path integral, which looks very similar to the previous one, where this map will be a continuous character. And well, I have again a detector of rationality. So it's going to be 1 if psi is a trivial character or 0 otherwise. So that's what, for example, one can build out of this path integral. There, I repeat different possibilities, but that's what I found. And so psi is trivial if and only if the art and motive associated to psi is going to be rational. And that's the main thing about this integral. So now I want to say what kind of information I have recovered from this. Well, it's actually a consistency check for Grothendieck and IOM conjecture, because it shows it's really consistent, everything there. There's a lot of beautiful arithmetic to consider, because since psi corresponds to an art and motive, this integral links the action of GT hat to the arithmetic of cyclotomic fields and other abelian extensions of Q. So and the good news is that the cyclotomic fields is something you can really work nicely with, which I wouldn't, well, yeah, which is not always possible when we consider elements of absolute Galois group. And well, so for those who have worked a lot with Fourier transform, the integral can be seen roughly as a Fourier transform of the harm measure on GT hat. And so such an approach reveals also a lot more about some geometric or harmonic properties of GT hat, which can be yet again something new to say about GT hat, yeah. Okay, and so that's the third part. So if there are any questions, it's now the right moment. But this is going to be about those paths I was mentioning, Cantorian paths, which are going to describe all the elements in the absolute Galois group. So it's kind of algorithmic, but since we know that it's Cantorian, well, a Cantorian computer program is going to go very, very long in time. So the best thing we can do using this, if we want to implement it on a computer, is the approximations, and I find it's quite well, interesting to consider, because you know exactly the path that you're outlining in absolute Galois group. or GT hat. So these are my Cantorian paths, and this is my cubic Matryoshka algorithm. So cubic is because we have all these cylindrical sets, you know, it's cubic actually, combinatorially speaking. And Matryoshka is because one open set is going to be in the other, and it goes like this for infinity, forever. And so here's my algorithm. So we know that for any element of Gall Q-bar over Q, there exists a unique binary Cantorian word. And so the root of the algorithm, so we start with the entire space Gall Q-bar over Q, which is huge. Now level 1 will be to partition Gall Q-bar over Q into two disjoint Clopin subsets, and so these guys are going to look like this: Gall Q-bar over K. K is some field extension. So I call them U0 and U1, that's two disjoint Clopin subsets. And so it's by induction, so you have a recursive step for each Clopin set US at level n, labeled by a given finite binary string. You can partition it into, again, Clopin subsets. And so, as I said, the good news is that you are actually really keeping track of everything that's going on, because you're going to choose one open set, which looks like Gall Q-bar over K, and then you're going to make a choice of another Clopin, which is already encapsulated in that bigger Clopin. And you're going to continue like this and really keep track of everything that's going on. And I find it very interesting. And for each G in Gall, we associate a binary sequence here, where globally it's 0 if G is in US 0 at level n, and 1 if G is in the other one. And so this procedure defines a unique binary sequence for each element in the absolute Galois group. The same holds for GT hat, because, as I said previously, we're in Cantorian setting. And okay, the inverse mapping holds naturally. So for a given binary sequence, we can define a corresponding element, which is going to be this huge intersection of Clopins. And, well, we have a bijection. So we map G to this infinite sequence, but the infinite sequence is again mapped to G, and we have this bijection. So this works also for p-adic integers. So the not so nice side is that the homeomorphism is not canonical. So if you want to build it for the absolute Galois group and for GT hat separately, well, you have to fix the rules very strictly at the beginning, how you are going to define this binary sequence. So this is maybe a not so nice aspect of having of this bijection that is not canonical. But this really gives a lot of information. And so, as I said, a similar construction holds for GT hat. And for example, it could be used using Vasily's GT shadows, because he has a very nice construction where you could actually work concretely, explicitly on those, well, on GT shadows. And a Cantorian construction could help, well, reveal, you know, like paths there. Yeah. So this is last statement that I wanted to mention, which is about well, trying to connect both binary sequences defined respectively for Gall Q and for GT hat, and trying to recover something from this construction. So we're going to have a finite Galois extension of Q. And so here I'm just using the classical setting. You have a normal subgroup of F2 hats defined as a kernel of the homomorphism from the étale fundamental group F2 hat to the Galois group of a given belly cover. And so this approach allows to say that there exists a Cantorian system of binary encodings for each element in GT hat attached to a finite Galois subextension of Q bar, verifying a certain number of properties. And this is very concrete, actually, so you can really follow what's happening in both worlds. So this, we start first with the Clopin encodings of Gal Q. So each finite Galois extension determines a Clopin subgroup, which is, as we have seen previously, encoded by some finite binary word, here, BK. Okay. And now, okay, we have, okay, so the main point is to show compatibility with GT hats. And while studying how my binary word that was defined in the world of Gal Q is going to be mapped to the other Cantorian word for GT hat. Okay, and so here we have that for each K, we have this projection. So it's natural projection here, this left-hand side. And we have this binary encoded actions that commute here. So GT hat goes to automorphism. So GK was just simply the quotient F2 hat over NK. Yeah, and so this is really like a bridge between the two Cantorian worlds, one for Gal Q, one for GT hat, well, passing through the BLE cover here. So that's what I wanted to say. Yeah, and I think I'm stopping here, and I apologize for all the coughing. Yeah, thanks.